Hello or welcome back. This is the first lesson, lesson 1 of the radioactivity topic for year 11 double science. Just to check you've got the right booklet in front of you for this topic. The front looks like this. Types of radiation. Can you please make sure that you fill in the front of the booklet? Pages are numbered. There's the list of equations and SI multipliers as always. Page 2 is for close the gap, marking, overall summary, page 3, and we're starting today on page 4. So please put at the top, lesson 1, structure of the atom and the date. Today then, before we go on and really look at what radioactivity is, we need to understand and make sure you've got a solid knowledge of the structure of the atom. It is something you would have learned before, certainly in chemistry, because radiation is all to do with the nucleus of the atom. That's why it's called nuclear physics and nuclear energy, relating to what you should know is the center of the atom, the nucleus. But let's take a step back in time and see what we know so far, both in terms of our understanding and also how the structure of the atom has been discovered over years. So I'll just highlight as I'm reading. It says here, look at how the understood structure of the atom has changed as new evidence comes to light. First person really to come up with an idea, a concept of the atom was Democritus, a Greek philosopher. And in 400 BC, roughly, Democritus thought that all matter was made up of solid lumps or atomos that could not be broken down any further. So this was his idea. A few things did happen in between, but mainly nothing really happened until thousands of years later, where J.J. Thomson came up with this plum pudding concept. He said that the atom was a solid sphere and tiny particles inside called electrons. So he came up with this idea, and the atom being of a positive charge and electrons being negative charge. So he wasn't far off our current understanding. Before we look in a bit more detail about the chronology of the understanding of the atom, just have a go at this. And you write down what you think will happen. If you were to throw a particle at the sheet of aluminium foil, what would happen to the particle? And I just want you to draw some arrows showing what you think is going to happen there. Is it going to go through the aluminium foil? Is it going to bounce back? So that's for you to do. So I'd just like you to pause the video now and just draw down what you think will happen. Doesn't matter if you're right or wrong. I just want you thinking. Pause the video now, please. Okay. So that was a chance for you just to think about what you think will happen. And underneath here, underneath the diagram, just write down why you think that's going to happen. And then pause the video again now. Let's look at a bit more detail about the historical timeline of the theories about atoms. You can see the picture here, look, Democritus, 400 BC, he came up with this idea of atomos, but didn't talk about anything inside them. Then we did have this gentleman, Dalton. He visualized atoms as tiny solid balls or spheres. J.G. Thomson, he came up with a plum pudding model in 1897, and then just over 10 years later, or 12 years later, in 1909, Rutherford. And we see Rutherford now as coming up with our currently understood model of the atom. And the difference there being that he felt that the atom was made up of a nucleus where the protons and neutrons are located, and most of the atom was empty space. We got two others here, Bohr and later on Chadwick, that added a bit more detail. To show that another way, what we've got here is Ernest Rutherford saying, I did an experiment that proved this idea was wrong. I called it the Rutherford scattering experiment. So what's he talking about? Well, it was this idea here of the plum pudding model. 100 years ago, people thought that the atom looked like a plum pudding, a sphere of positive charge with negatively charged electrons inside. The charges being the plums in the pudding. Now what was found was that when the alpha particles were emitted towards a thin gold foil, we found that the majority of the particles went through. Only a few were deflected back. And importantly, what that told us was that the most of the atom was empty space. So the conclusion, an atom is made up of a small central nucleus, we can see here in red. This isn't the scale. Surrounded by electrons orbiting the shell. So the atom, as we now understand it, is like this. You've got protons and neutrons in the middle. A proton has a mass, same mass as the neutron. The proton has a positive charge. The electrons have a very, very small mass, a 2,000th the size of the proton, and has a negative charge. And if we look at that in the table, the proton has got the relative mass of 1 and a positive charge. A neutron, relative mass of 1, it's got 0 charge. Look at the spelling of neutron, neutral. An electron has got a negative charge. We say relative mass. It's got there 0. It's actually a 2,000th the size of the proton. Remember in year 10 we learned about the electricity, and electricity was a flow of electrons. That's where the word electricity comes from. In future lessons, I know we've done this in chemistry, but we're doing a bit on this as well, that in the periodic table, the number at the bottom is the number of protons, and the number at the top are the number of protons plus neutrons, or number of nucleons, because they come from the nucleus. Turn over to page 5 in your booklets, and what you've got at the top here is that same experiment, that famous experiment, shown in a different way. It says, so this is what the two scientists called Rutherford, Ernest Rutherford, and the scientist that he worked with, Marsden, did. They fired positively charged alpha particles. You won't know what alpha particles are at the moment. We'll learn a bit more about them again, but basically an alpha particle is the nucleus of a helium atom. It's got 2 protons and 2 neutrons, because we've just looked at the symbols or mass and atomic numbers for a helium atom. That's the 2 protons, and that's 2 protons plus 2 neutrons. So a helium nucleus is a helium atom without the electrons on the outside. So because you have the negatively charged electrons on the outside, there's an overall charge of plus 2. Now that's important because underneath what we'll find here is these alpha particles are fired at the thin gold foil, and you can see that one's gone straight through. This one here will get deflected, and the reason it gets deflected is because if we were to zoom in on this area here, what you've actually got is a lot of protons inside the nucleus giving it a positive charge. You've got this alpha particle that's got 2 positive charges there, and when it comes close it gets repelled away because 2 positive charges cause a repulsive force. Now you don't need to remember all of this for the exam in year 11. You don't need to remember the experiment. You don't need to remember the chronology of the discovery of structure of the atom. But the reason we're learning about this first is that you understand how we know about the structure of the atom and the nucleus and so on. So what I'd like, so don't worry about this too much if you don't fully understand it. It's just a way for you to hopefully get a better understanding of the structure of the atom and how it is we know about it. So you can just finish off now by just drawing a few of these. Like this alpha particle here, it has deflected back away from the gold foil because it's hit the nucleus directly, and that one's gone through and that one's gone through. The conclusions underneath. What conclusions about the structure of an atom can you draw? 2 things. Firstly, an atom has a positively charged central nucleus. That's number 1. Number 2, an atom is mostly empty space. Let's put that into context. They say if we were looking down bird's eye view, and this was the Millennium Stadium, or now the Principality Stadium. Alright, so here's the pitch. And there's the lines on the pitch, halfway line, and so on. And there's the rugby posts. Looking down from the bird's eye view. If this whole thing, if you think of this whole thing as the atom, the actual size of the nucleus would be about the size of an orange in the middle of it. So if we take all this away here, that green dot in the middle is the nucleus, and everything inside the red circle is the atom. What you've got flying around inside the atom, of course, are tiny little electrons that go around the outside. So an atom is mostly empty space, and also negatively charged particles orbit the nucleus. However, from this experiment here, it's the first two, 1 and 2, is what we can conclude from the experiment. Turn on then to page 6. Looks like this. Just a reminder there, an atom is made up of a very small, positively charged nucleus. That's in the middle here, with electrons orbiting around the nucleus. Draw out this nuclear model atom. Notice that the protons and neutrons are of a similar size. The electrons are much smaller, about 2,000th the mass of these nucleons. Include a key to show the 3 particles. Okay, well, I'm going to do one in a moment, and I'll draw the atom underneath, and then what you have to do is describe the nuclear model of the atom, and this part here is for you to do. Right, so that'll be a teacher assessment part. Teacher assessed. And what you need to do in that part there is make sure you use all these words. So for example, you'd start off by saying the atom consists of a central nucleus that contains nucleons, which are protons, positively charged protons, and negative and neutral, I should say, neutral nucleons. Protons have a positive charge, neutrons have no charge. The atom is mostly empty space, and electrons orbit around the nucleus, and the electrons have a negative charge and have a mass of 1/2000th the size of a proton and a neutron. I could have crossed out neutron earlier. Something like that. Okay, so you write that underneath here. But before you do that, you draw out your nuclear model. Now, you could draw a hydrogen atom, a helium atom. I'm going to draw a helium atom because we've already talked about the helium atom, in that it's got 2 protons and 2 neutrons. So I've drawn in the 2 protons. I'm now going to draw in the 2 neutrons, and around the outside, I'll use a different colour, I'll draw in 2 electrons. I'll put a key to the side. I'll do it well to the side of the atom. And the other thing I could do here as well is just show that just this dotted line shows that the electrons are orbiting around the central nucleus. A quick key then, I'll do it to the side here so as not to confuse with the atom itself. So key, positive, that's your proton, P for positive. I got my neutron. Remember, NEU, neutron, is neutral. And then we've got our negative electron. You go on then and, as I mentioned earlier, write out your description of the nuclear model of the atom underneath. And then turn on to page 7. There's some questions for you to do underneath, but before that, a little bit more information. Atoms usually are neutrally charged overall. They have no charge. In other words, the number of electrons equals the number of protons. And we can see that above in this atom, the helium atom above. We've got 2 protons, which are cancelled out by the 2 electrons. given an overall charge of 0. Atoms may, however, lose or gain electrons. So if we had this atom here, if this electron went flying off away from the atom, then we wouldn't have a neutral atom anymore. If that was just one, we've got a charge of -1, that would mean that would equal an overall charge of +1. So that atom would have a positive charge on it. Now we would call that an ion. If an atom gains or loses electrons, it becomes an ion. If it gains an electron, it becomes a negative ion. If it loses an electron, it becomes a positive ion. Oh, excuse me there a second. This is just shorthand for positive. And this is just shorthand for negative. You might see that written down in books. It says look at the 3 following nuclear model atoms diagrams and then answer the questions. So we've got A, B and C. What particle do the large dark circles represent? Now I'm going to do question 1 and 2 and then I'll leave the others for you to do. What particles do the large dark circles represent? Well, if you think about it, if that and that are protons, then the large dark circles must be neutrons. What 2 particles are ions? Well, if we look at C, we've got three protons and we've got 2 negative electrons. So that means that it's got an overall charge of +1. So C is a positive ion. If we look at A, you've got 3 protons and 3 electrons, cancels out. It's not an ion, it's an atom. If you look at B, well, you've got 4 electrons. There we are. 5 electrons. And you've got 3 protons. So if you've got 5 electrons and you've got 3 protons, then it gives you an overall charge of -2, -2. So that would be B is a negative ion. I think then you should be able to do 3, 4 and 5. This will be a self-assess. So pause the oops, I can't spell pause. Pause the video now. Okay, you should have paused the video and you should have written down your answers. So compare your answers to these. Explain which particle has no overall charge. Well, we've already looked at that earlier. It's A. And the explanation is because it has the same number of protons and electrons. Same number of protons and electrons. Let's look at that again. Yeah, 3 protons, 3 electrons. Which particle is negatively charged ion? Oh, we've already answered that up above here. B is a negatively charged ion. The explanation: it has 5 electrons and 3 protons. 5 electrons and 3 protons. Name a particle that is not a nucleon. Well, if you think of it this way, this is the nucleus. So everything inside the nucleus is a nucleon. Anything outside is not the nucleon. So electrons are not nucleons. So the answer there, electron. Well, that's the end of, oh, by the way, just mark those right with a red pen if you got them right, or correct them with a red pen if you haven't got them right. And that's the end of lesson 1. Make sure you do the plenary assessment on the study zone. See you next time. Bye.